Hi guys. Today we're going to take a little bit of time to look at motion graphs and motion maps. This is going to be an introduction for my class. We've done a little bit. Our lab today was with a electric car or a battery-powered car that traveled at a constant velocity. And much like in this graph right here, you are graphing time on the x-axis and the position on the y-axis. Now this one just happens to be a man walking out the front door, but you'll notice that this line looks very much like the line from your lab today, in that it is a straight line. Okay, just like with the car, that meant that it was a constant velocity. Hopefully you noticed with the tractor that the y-axis being position and the x-axis being time, that when you did slope or rise over run, that as you went up and over, just like this, that's the slope, right? Rise over run. That would be rise, which the units are meters, over run, which the units are seconds, meters per second, which just happens to be velocity. Woohoo! So that's what the slope is of a position versus time graph. Okay, so that'll be important as we start to look at some of these other things. So you can actually get a velocity by looking at your position versus time graph. Okay, so what we're going to do is we're going to go ahead and talk through these things and look at the motion map, and then I'll work through an example with you. Okay, so this one we can see already has a constant velocity. Okay, I can actually get that constant velocity by working through. I know my rise goes from 5 up to 8, so that means it's going up 3 meters. And then the run is going from 2, 3, 4 to 5, which is another 3 seconds. So 3 meters divided by 3 seconds is 1 meter per second. And so that is my velocity. You'll notice that if I do the slope anywhere else, let's say I decide to do it right here, rise and run, it's 3 over 3 again, which means that my velocity is constantly 1 meter per second. And so if I come over here to my velocity graph, if I want to draw the velocity in, then I would draw a constant line at 1 meter per second. No matter what time it is, my velocity is always 1 meter per second. So I'd go right here to 1 meter a second, and I would draw my line just like this, showing that it's remaining constant, and the velocity is always 1 meter a second. Notice that in this graph, velocity is on the y-axis, and so that's showing that I have a constant velocity of 1 meter a second. Okay, so hopefully that kind of makes sense a little bit, and that by using the slope, you can get the velocity. Okay, one other kind of neat thing is that you can get your distance traveled by taking the area of the velocity graph. And so if you go from 1 down to 0, right, that's a height of 1. And then if we count the time, which is 10 seconds, so that's a length of 10, right? So 10 seconds. And this is 1 meter per second. So if we find the the area of that rectangle right there from 1 all the way down to 0, okay, that would be 1 times 10, so 1 meter per second times seconds. The seconds will cancel out, right? 1 meter per second times 10 seconds. The seconds will cancel out, leaving us with 10 meters. And you'll notice if we go back to our position graph that I started at 3 meters and I ended up at, oh my goodness, I ended at 13 meters. That's 10 meters. Woohoo! Yeah! All right. So you can see how the two graphs are interrelated. We'll be looking more at that as time progresses, but that's the basic idea. Now down here at the bottom we've got a motion map. Now what the motion map is it's showing us particular points in time and the position and or velocity at those points in time. And so at time equals 0, my position was 3 meters. So I just put a point right there at 3 meters. Okay? At time equals 2 seconds, so 2 seconds, my position was 5 meters. So I put that point there. And you go through and you put points at each of those positions. And that shows me, I can see, since all the points are the same distance apart, that every 2 seconds I'm traveling the same distance. And so I have a constant velocity. You can see that by looking at the position versus time graph. If the points were getting farther apart, then you would know that your object is speeding up. The point should always be a consistent time period apart. These are all 2 seconds apart. Okay, we can do a similar thing with velocity. Okay, now this is actually wrong because as we know, we just did this and we know it should be 1 meter a second. So these should all be 1 meter per second. Okay, so if you would on your worksheet, go ahead and fix that. Make sure that these are all 1 meter a second. But the idea is velocity is a vector. We've talked about vectors, and so we've got that point. It's going 1 meter a second in this direction. At 2 seconds, my velocity is still 1 meter a second. So there we go. At 4 seconds, I'm at this position, and my velocity is still 1 meter a second. So same position. And so the velocity graph is actually still showing position, because it shows at what point I'm at, but it also shows the velocity. You'll notice that each of the arrows is the same length, and the length demonstrates the magnitude of the vector. And so the length of the vector shows that it's 1 meter a second. If it were to be speeding up, then your arrows should be getting longer and longer. If it were slowing down, they would get shorter. If you started doing velocity in the opposite direction, obviously the arrows would point the other direction. Okay? So you'll notice that as the position changes, then the velocity vectors will move where they're at. Okay, so hopefully that kind of makes a little bit of sense. Let's talk through question number 2. All right, so in the first problem, when he was walking away from his front door, we said that was a positive velocity. He was increasing his distance away from the door. So now in this question number 2 here, it's going to be different. Okay, so the man started out 16 meters from his front door. So at time 0, he is at 16 meters. And he walked toward his door at 4 meters per second. So each second that passes, I'm getting 4 meters closer to the door. So after 1 second, I'll be another 4 meters closer. After another second, 4 meters closer. After another second, right? And so you should be able to get this idea. Okay, and then we want to draw a nice straight line right there. So here we go. I'm actually going to use my ruler. There we go. There's my distance versus time graph. Now, it doesn't obviously stop there. If he continued in, then it would continue to go this way because I'm still going in that negative direction. Okay? Now, you'll notice that the slope of this line is down 4, right? Down 4, which is negative 4, over to the right 1. So negative 4 over 1, which is negative 4. But we already knew that because the question gave us that he's traveling at 4 meters per second towards the door, which we have defined in the previous problem that towards the door is the negative direction. So in this case, my velocity would be at negative 4, and he's going a constant velocity. Now, I'm going to go ahead and draw it right there at negative 4. Okay. Make it a little bit nicer line. There we go. And so that's showing that he's going constantly negative 4 degrees. Meters per second degrees. We don't even need angles. Okay, so that's what's happening. Now, let's look at our motion map here. Okay, so let's start with when it's at time 1, he was at 16 meters. So 16 meters. Sorry, that's time 0, right? Time equals 0 seconds. We can do it like the other one before where we were doing every 2 seconds. You can do every 1 second. It doesn't really matter. Let's go ahead and do 2 seconds just to be consistent with the other graph. So at time 2 seconds, he was at 8. So now we're going to be here. So that's time equals 2 seconds. And then at time equals 4 seconds, here's 0. Okay. And so then it went off the graph, and so it will go off my number line. Now, if I had a longer number line, I could keep going, right? Or if I said, okay, now he stopped, then I could just draw it continuing that way. Now, if he started walking the other direction, then I could just put the points above here or down below, just to show that I understand that he's going back the other way. But you can see how the labels and the positions show that I'm going the same distance every 2 seconds. Okay, let's add in the velocities. So the velocities will be at the same point to show that it's at 0 seconds, but the velocity is negative 4. So I'm going to go negative 4 meters per second. Okay, note that this doesn't have to be 4 spaces on your position graph because this is position, this is a distance, it's not velocity. So as long as I'm consistent with my vectors. Negative 4 meters a second. At 2 seconds, he's still going negative 4. So as long as my vector is the same length as the one as before, then it's okay. And then at 4 seconds, he's still going negative 4 meters per second. Okay, and so there you go. There's another example. Hopefully that's enough to kind of get you started, and you'll be able to finish the last 4. Good luck, and if you have any questions, be sure to drop in and ask. See you guys later.